Hello and welcome to today's video. Today we're going to be taking a look at logic level converters, trying to get an understanding of what they are and what they do. So to help us get started, I'm going to jump into a schematic on KiCad. So let's just look at that. Okay, so here's the prototype board that I've been using for a couple of my videos, where we have a Arduino Nano in the main supply, and then we have a I2C interface bus with 4 I2C devices, an EEPROM, an LED display, real-time clock, and an atmospheric sensor. Now, I specifically set the I2C bus to 3.3 volts because all of these devices support 3.3 volts. But sometimes you get a situation where one of the devices doesn't support any of the voltages of the other devices. So let's take an example. Let's pretend this OLED display, this SSD 1306 display, doesn't actually support 3.3. Say it only requires 5 volts. What can we do? Well, in that situation, you could pick or create another I2C interface and set that one to be a 5 volt supply, but you may be limited by what pins you have available on the microcontroller. So another solution is to use something called a logic level converter. Now, you can basically buy this as a module, but it's a very simple circuit to implement. So I bought this one from eBay. I'll put a link in below to show the part number. But basically on here, this actually has 4 level converters. So it can convert up to 4 different lines. Now, I'm going to insert a... come on. Wait for my computer to wake up. Okay. So on here, I have created a symbol for a logic level converter, particularly this module. So here we see, if we actually look at it, we basically have an input side and an output side, an input voltage and a secondary. I shouldn't say input voltage. We basically have side A, this LV side, this HV side, and then we have this LV side voltage, and this side HV side voltage and ground. So, excuse me. What this enables us to do is actually have 2 different logic level systems on either side of this device. So, if we say at the moment I have a 3.3 volt I2C bus and I want to adapt it to allow a device which is 5 volts. Let's do this as an example. I'm going to take my OLED display. Okay, I'm just going to rotate it so it looks a bit nicer. Okay, so actually, yeah, do it that way. That's a bit annoying. Anyway, so let's pretend this only supports 5 volts. So if I do 5 volts and type, and okay. So I've now got a display which uses 5 volts. Now I need to adapt this to go to 3.3. So what we can do is if I power the right hand side of this logic level converter with 5 volts. So I'm just getting this out so you can actually see a bit clearer. Okay, so what I'm now going to do is I'm going to power the left side with my 3.3 volt supply. So on the left side we have a 3.3 volt logic system, and then on the right side we now have a 5 volt logic system. So what we can now do, doesn't matter. Sorry. They didn't line up perfectly, doesn't really matter. Okay. So what we can now do is on the right side connect the 5 volt side. So this is SDA. Now it goes through, so I want to connect this side to my SDA line, and this is now going to be my low side clock. So I can do something like this, and this will connect a 5 volt logic system to a 3 volt logic system. Now that's basically how it works. The only thing to be careful of if you're using this now with an I2C interface is don't forget to add some more pull-up resistors. So remember, we have to have pull-up resistors in order to drive the signal to a 5 volt rail. On this side, these are only being pulled up to 3.3. If this side is going to be an I2C interface, these need to be pulled up to 5 volts. Now this is something which can be easily overlooked, but it is crucial if you want the signal to work correctly. So now what I have is I have a single I2C interface bus, but it is driving 3 volt I2C devices, and it's also driving 5 volt I2C devices. So that's a little bit about how we use it. Let's switch over and I will show you it working in real life. So see you in a minute. Okay, so we've now taken a look at the logic level converter on the schematic to see how we're going to connect it. Now, as I don't actually need any 5 volt I2C interface, I've just mocked something up here. So what I've done is I've taken the 5 volt voltage from the Arduino Nano and brought it over to this bottom power rail. Same with the ground. So the I2C interface that I'm currently running on this side of the board on the top half is a 3.3 volt I2C interface. What we're going to do is we're going to use the logic level converter to convert from 3.3 up to 5 volts. So as I say, we've got the 5 volt rail in place. The only thing I'm doing on the 5 volt side is I'm adding a pull-up resistor on the 5 volt side. Otherwise, it's going to be trying to the pin is going to try to float. We don't want that with the I2C interface. So we want to add pull-up resistors on this side of the logic converter, as well as having pull-up resistors on the 3.3 volt side. So I've just put in a single pull-up resistor. If we're doing a full interface, we would actually want to have pull-up resistors for both the clock line and the data line. But as I say, this is just a demonstration. So what I have here is I have the both the 3.3 and the ground side connected up to 3.3. The 5-volt side, I've got 5 volts and the ground on the 5 volts, and the pull-up resistor to 5 volts. What I'm now doing, I'll just use one because I've only got one resistor. So I'm going to take the clock line, which I'm going to use this blue cable to bring the clock signal, the 3.3 volt clock signal, across to this side. And we're going to take a look at it and the scope, but just to confirm the voltages. So I'm just going to double check. So on the 5 volt side, it's 4.5 volts, it's close enough. And then on the 3.3, we've got 3.29, perfect. So 3.29 and 4.5. So we've got the low side and the high side. So that's going to allow us to see the difference. So let's get that out of the way. Okay. So we have the logic converters. We've got a 5 volt pull up resistor. We've got the signal coming across. We should be good to go. I have a little demo sketch loaded, which is just my dice rolling program, where you can just roll the dices. Now, if I take a quick look at my sketch, I've just been playing with it. Currently, I've got my I2C interface set to a, I've got the I2C interface set to 100 kilohertz. So let's just hook up the scope and we can take a look. Okay. So grab my channel 1 ground, and I'm going to hook my channel 1 to the 3.3 volt side. Channel 2 again. Try not to short out the power supply. And then on the 5 volt side, I'm going to hook up channel 2. So I've got my channel 2 signal I'm taking from HV3, and I'm using LV3 on the other side. So LV3 through the logic level converter to HV3. So we have everything hooked up. So let me just do a send a signal. And voila, okay. Let me save that to disk. So we can see on the low side, we can see our 3 and a 3.3 volt signal. And on the high side, it's dropped a little bit. It's like just over 4 volts. But it is significantly higher than the 3 volt side. The reason it's a little low is actually the amount of power coming through the Arduino Nano is a little bit limited. As I say, I've got a few other little things, but it's not really regulating the 5 volts. It's taking the 5 volts from my one of my hubs, and that isn't actually outputting a really good 5 volt level. Let me see if I can use a better 5 volt signal. Okay, bit of improvisation here. It's almost as if I had this planned, but I didn't. So I have a power supply module for this board. Just make sure, always double check. 3.3, negative, positive. Oh, okay, no, has to go on that way around. Always make sure you have polarities correct, positive, negative, and I want this one to be 5 volts. Okay, so the mark positive, negative, positive, negative. That's something you don't want to get wrong. So I'm not going to take the 5 volts from the Arduino anymore. I'm just going to use a dedicated power supply. Okay. So let's see if this gives more power. Should do. Okay. Let's bring this back in and let's see what we're getting now. So do ground. Come in. Okay, so there I've got a good solid 5 volts, and again on now I've got a good solid a good solid 3.3 volts. Much more power than I had available before. So that's golden. Okay, so we hook up the signal. So this is the ground, and signal. Okay, so I've got channel 1 hooked up to 3.3 volts, channel 2 to the 5 volts. Got something wrong here. Something wrong. .3, 5. Power. Oh, okay. Okay, I know what I've done wrong. I've disconnected 5 volt supply from the Arduino. Originally the 5 volts was coming through the USB. I'm now not using that. I'm using this 5 volt rail. So obviously the Arduino powered off because it didn't have any power. So I'm just going to provide power to the 5 volts. Okay, so I just got power back to the Arduino. And surprise, surprise, it works a lot better once you have power going to your microcontroller. So where were we? Okay, let's go back. I've got the signal, 3.3, 5 volts, 3.3, 5 volts clock. Okay, let's set the capture. Okay, there you have it. That's great. So we actually have the 3.3 volts on the yellow signal, and the 5 volts is the upper green signal. Now our clock speed at the moment is set to 100 kilohertz. It's actually interesting. The 5-volt I2C clock actually looks a bit cleaner than my the 3.3 volt. 3.3 volt has a slight curve, you can see. That's probably due to the capacitance. When using a prototype board, one of the key issues is it's not great. There's a lot of metal inside it, and that can create stray capacitance. And that stray capacitance can do lots of unwanted things, like rounding off edges of signals. So, but I'm not too concerned. It works fine. So let's try the next thing. Let's see how fast the logic level converter can go. So let's bump it up to 400 kilohertz. Uploading now. Okay. In order to upload, I have to plug in it to upload. Okay, so we connected it. Tools, all content. Okay. So again, uploading code works a lot better when you connect the microcontroller. I just don't like having the microcontroller power as well as an external power source. And the site's done. It's uploaded. So we've now changed the I2C bus to 400 kilohertz. So let's power up. So we're now powered. And let's do a capture. Okay, and there we have it. So save that to disk view so you can see an image on the screen. But basically we have now the 5-volt side working perfectly, and the 3-volt side is also working, although it has a slightly rounded signal. But it still functions perfectly. There's no glitches at the moment. I might consider lowering the pull-up resistors to try to overcome that rising edge. But that's for another day. Today I'm going to leave the video there. Hopefully you get to see and understand exactly what a logic level converter chip does. And thank you for watching. Have a good day.